Hi everyone. This is Sarah and my group mates Will, Rita, and Nick, and our experiment is on airborne PFAS from firefighting foams. So our motivation for choosing this experiment is that per and polyfluoroalkyl substances are a group of persistent synthetic chemicals, and they are widely used in firefighting foams because of their surfactant properties and their thermal stability. Lots of research is focused on PFAS contamination in soil and groundwater, but there's less research about presence and behavior in the atmosphere, and especially in the realm of foam application. So foams generate aerosols and vapors that release PFAS in the air, and this leads to atmospheric transport, inhalation exposure, and deposition on surrounding environments. So our goals and objectives for this experiment is to quantify airborne PFAS concentration during firefighting activities and in ambient air following their application, to identify predominant PFAS species and to compare between foam types and conditions, and to assess how concentrations change over time and distance. Ultimately, we would like to provide data to inform regulations, foam formulations, and safer occupational practices in firefighting. So, in our literature review, we found that PFAS are manufactured chemicals that are found in many industrial and consumer goods. Um, and due to its widespread use, they're often found in the environment and even in the bloodstreams of people and animals. So, PFAS is found in the aqueous film forming foams or the Class B foams that help fight liquid fuel fires. So that would be um, the fluorine containing foams can be used as an alternative, but AFFS are more effective at containing a fire. And we also found in our literature review that firefighters have a greater risk of cancer due to their exposure to hazardous chemicals that they encounter day to day in their role. So they have a 9% higher risk of developing cancer and a 14% higher risk of dying of it. So emerging evidence also links PFAS exposure and an increased risk of certain cancers like kidney and testicular cancer that are elevated risks for firefighters. And some of the other known health effects from PFAS exposure include decreased fertility or increased blood pressure in pregnant women, reduced ability to fight infections, and increased risk of cancer, especially prostate, kidney, and testicular cancers, increased cholesterol levels and risk of obesity, and developmental delays in children, such as low birth weight, behavioral changes, bone variations, and accelerated puberty.
So the main question we are trying to answer is what are the concentrations, speciation, and particle vapor ratio of PFAS in air after using the firefighting foams? And our hypothesis to answer that question is the use of firefighting foam produces measurable airborne PFAS more than the background levels already present. So our research approach is to have the firefighters wear wearable pump and sampling trains, and we'll place these pumps and sampling trains close to their chest area so it is close to kind of where they'll be breathing it in, close to the user, and also comfortable for the user to wear for a prolonged period of time. We also want to test different kinds of firefighting like Class B firefighting foams or AFFF. There is a range of what they're made from. Like they can be made from a mix of surfactants, budding agents, and stabilizers. And it allows for a blanket over the fuel, preventing oxygen from reaching the fire. And there's many different kinds like alcohol resistant, fluoroprotein, and more, just depending on what type of foam it is and what it's trying to fight. There are multiple. We'll do multiple trials during a training exercise where the foams will already be in use anyway, and we'll just be sampling what they're using at that training exercise. The fire will be controlled and simulated by the department, and there will be no unnecessary exposure required, so it doesn't put them in increased risk. And then we'll use gas chromatography and mass spectrometry and liquid chromatography and mass spectrometry. So to further talk about the difference between the liquid chromatography and gas chromatography, we'll separate the sample into particle bound and vapor phase PFAS. Um, these are pretty similar into a certain step. Both gas and liquid chromatography has a sampling step, an extraction, a cleanup and concentration step, and then the sample is injected into the column. And then once that happens for the liquid chromatography, it goes through a stationary phase, a separation phase, a detection phase, and then it does not have a vaporization phase like gas chromatography, and it goes into a pressure phase. For the vapor phase PFAS using the gas chromatography and mass spectrometry method, it goes after the sample injection into a vaporization phase, a carrier gas flow, a column heating, then into the separation phase, and then detecting the different contaminants. So the instruments needed for our research is wearable pump and sampling train with a filtered cassette in a particle-bound PFAS and sorbent tube to get the vapor phase PFAS. The gas and liquid chromatography method, which is an analytical separation method where an inert gas, carrier gas, is used to separate volatile compounds. The gas chromatography will be used for the vapor phase, and the liquid chromatography will be used for the particle-bound phase, which will also use to solvent extraction to remove the PFAS from the solid matrix. And then we'll also need mass spectrometry to measure the different components.
The function of gas chromatography is an analytical separation method where an inert carrier gas is used to separate volatile compounds. There are two phases, the mobile phase and the stationary phase. The obtained sample is objected to a sample port, which is then heated and vaporized. The sample is pushed through the column using an inert carrier gas, typically helium, and is separated into components. Once the sample is pushed through the entire column, the mass spectrometry quantifies the components in the sample. Different gases have different affinities for the stationary phase. Liquid chromatography. The function of liquid chromatography is a process of using a liquid solvent to separate compounds. The liquid sample is pumped through a compressed column. Components move at different speeds based on the rate at which they interact with the mobile and stationary phase. Thus, liquids are separated by composition. Mass spectrometry. The function of mass spectrometry is to identify and quantify chemical substances based on their mass to charge ratio. In this experiment, we identify PFAS that have been isolated by chromatography. In the process, in preparation for testing, PFAS are extracted from samples and confined to a high concentration. They are then ionized so that their electrical charge can be measured. PFAS are passed through the mass spectrometer, moving different distances based on their mass and charge. wearable pump, and sampling train. Function. Wearable pump would be downstream and pull in a controlled flow of about 1 to 2 liters per minute. Sampling train collects particle-bound and vapor phase PFAs. The filter cassette would have a quartz fiber filter, less likely to contaminate the sample and handle heat well. This catches particle-bound PFAs, for example, dust and aerosols, and allows vapor phase PFAs to pass through. A sorbent tube is downstream of the filter cassette for vapor phase PFAS to deposit. Measurements. Massive PFAS, both as vapor and particle bound, phase distribution, and time of exposure. This is relevant to our experimental design because it measures the occupational hazard of firefighters using foams.
So in order to analyze and interpret our expected data, we would present our data as a comparison between the levels of PFAs found in firefighting foams to the safe levels of PFAs, compare between different kinds of Class B AFFF foams, compare the standard error from the data collected from each method to determine which has the strongest precision, evaluate the results on a 95% confidence interval to determine if the data is statistically significant. Some quantification methods used to determine levels of PFAs include the percent peak area method, where we use the area under a curve of a target component to determine changes in concentration of a known sample. The absolute calibration curve method, or the external standard method, uses a sample of a known concentration to prepare a calibration curve, which is used to determine components in an unknown sample. The internal standard method, which calculates the concentration of a target component using the relationship between peak area ratio and the concentration ratio of the target component in an internal standard, and the standard addition method, which uses an unknown sample and spikes it with a known amount of target component, and then uses the difference between detected peak areas to determine the quantity. So for our expected results, we would expect the PFAs to be present in the firefighting foam. We would expect increased levels than what is considered an acceptable level, and the acceptable level is around 2 nanograms per liter. Um, we we would identify the predominant species of PFAs. We would determine the best foam type and condition, and we would quantify the effects of exposure during prolonged periods, or correlate a relation between time exposed and mass of PFAs collected in the sample. Implications to stakeholders include PFAs being a carcinogen. So that means any dose puts those exposed at risk. However, higher doses lead to higher risk. If the PFA levels are as high as expected, stakeholders have a higher chance of developing health conditions such as cancer, as we've mentioned before. As the predominant PFAs species is identified through this research, solutions to reduce that specifically may need to be implemented. The best foam determined based on having the least amount of PFAs can be an alternative to other foams if it's below the acceptable level. And there may need to be future regulations on PFAs and firefighting foam or new PPE. And these are our sources.